So which model do we study? Out of three, yeah, like 1,000 methods and 3 models.
The oscillation one?
Okay.
American side.
Yeah.
That's going first phase. That's going
Okay.
on.
Okay. And do you know how to answer the like second last question on the Wednesday thing, like 5 examples of oscillator?
Yeah.
Are you going to keep it hidden so that you don't give credit to your classmates, or you
Oh,
can
that is.
verbalize it?
Okay. I don't know. Examples. I think you mentioned one in class.
And you need to list 5.
Yes.
Huh?
You wrote them on the board, right?
I'm not sure if you wrote all 5. Can you list them? I don't care. I don't demand you to remember it individually, but it's quite easy question.
It was the one over the square root of.
No, examples.
Examples, just
Oh,
back to real life,
Oh, okay.
like pendulum in the cuckoo clock.
Yeah.
Okay, I thought you Oh, were that's talking an about like. example?
Why not?
Oh.
You can, or plasma and gold nanoparticles. Plasma. When electrons just go forth and back, oscillating.
Okay.
So I think in Dr. Young's, I can't pronounce his first name, but you know.
I mean, neither. Don't worry about it.
Don't you?
Yeah. It's okay, we know Yan.
I know Seth said it during group meeting the other day, but I always call him Dr. Yan.
Yeah.
So you, if one fabricates nanostructures, not semiconductor, but gold metals, there is no gap, right? The common gap is 0 in metals, or close to 0, but they still optically active, and the French medieval churches have this wall, like when the sun comes through the windows, they have different colored glass.
Yeah.
And when put it by melting glass with gold nanoparticles, there was a medieval technology, and one can control the color by size. But it is not as we studied in particle and quarks, the mechanism for color of metal nanoparticles is plasmas when electrons collectively move forth and back, for example. Your favorite example is our elements of electronic circuits, right?
Yeah.
Oh, yeah.
What else? What else?
Mention F5. Yeah. For real.
Just oscillations of molecules. Right?
Yeah, so we just.
Okay. Okay. Anything else?
The spectroscopy. Roman.
Okay. Anything? Huh?
Does that count?
Well, spectroscopy is a way to measure it, but which object oscillates? It's still like vibrations of different levels can oscillate.
Those oscillates.
I don't know, a child on a swing.
Yeah, good example. The surface of water, on the particle. Right? What about electromagnetic radiation? So we discussed the LC circuit, right?
Yeah.
But it was more something we can touch with our hands, like circuit, electrons go forth and back. But if you do have electromagnetic wave just in space, or electromagnetic wave engaged between 2 mirrors, what do you think about it?
Keep bouncing back.
Yeah, mirrors, like mirrors, electromagnetic wave between them, and maybe the active medium. How do you call it in modern science? And sometimes this thing is used for pointers.
Laser?
Yes. Electromagnetic wave between mirrors and then active media that donates energy to this. So
Laser is.
yeah, light amplification, blah blah blah. So electromagnetic wave is electric and magnetic field, right? They oscillate, and they oscillate with any frequency and do plane waves in space. But if it is enclosed in a resonator between the mirrors, then it oscillates with certain frequency that is like each laser has its own frequency. Right? Right. 600 nanometers, which would be whatever. I don't want to make her yellowish color. And then you can control it by size of the longer distance between mirrors, typically longer wavelengths.
Makes sense.
So electric field in the originator for invasive electromagnetic field, it behaves also as an oscillator. And a lot of theoretical considerations of harmonic oscillator were applied to this oscillator and rewarded as like novel terms. Although it looks like abstract concept to torture young minds. What did we do last time? I remember that we did maybe 10% of original plan, but what was it?
About, I think we tried to derive the number operator. We talked about the number operator, we talked about.
All correct, but can we summarize it in like less colloquial words? Just generally, summarize what we were trying to do.
Stop.
Yes.
Like that.
I remember that equipment was not working. And I was trying to write something on the board, but which objects did we play with on the board? Yes, matrices. And what was the meaning of that matrix?
Or are we taking in like an operator?
Yes.
Turning it into a matrix?
Yes, exactly.
From like vector.
From a continuous, from differential operator to a matrix. Yes. Thank you, Fred.
No problem.
You're 1 year more senior than the rest of the class.
Yeah, in theory, yeah.
Okay.
Yes.
They have time to catch up after you.
Sure, yeah, they'll,
We'll get there one day, I hope.
they don't
Be at your
feel like
level.
a year senior to anybody.
How did you like him?
I'm way off the subject.
No, I'm just trying to. figure
I
out-
took archaeology, not anthropology.
Pick so,
did you?
pick so.
For anthropology, you need that
Okay.
and Roman to read the.
Don't take archaeology, it was boring as hell. Boring as heck.
111.
We're recording. Sorry.
Let's keep talking about matrices. Yeah. Matrices.
It's not matrices.
Oh, matrices, let's talk
I
about.
was so surprised, like, if we are going to speak about matrices, maybe we should stop recording. Okay,
That time.
which operator did you convert into a matrix?
Evolution.
Try once again. The list of operators that we know is not very long,
Yeah.
But it's not the,
not the evolution. Evolution is too complicated.
sounding
Yes,
one?
explain.
Annihilation.
Annihilation of creation, right?
I like that.
And do you remember?
I like it.
Do you remember how to create creation operator out of position and momentum? Or you know it in theory.
Yeah,
right?
we talked about it, that's the thing you're right.
Can you follow Brad and explain how to create creation operator out of position and momentum without details? Like he told, we were converting differential operators into the matrix. Now, how to create creation operator out of position and momentum?
There was an equation for it.
Yes, and
We
what?
turned it into a summation.
Yes, exactly. Summation, or if you don't remember whether plus or minus, you can add superposition of position and momentum operator gives creation and equation operator or linear transformation. Linear because you don't have squares. Each of them come in the first power, and then it sounds very mathematical.
Nice.
If your math instructor after what you were doing on physical chemistry, working on linear transformations. Okay.
So impressed.
So there was a plan to show how to combine creation and equation operator together and get a number operator, which I skipped for the sake of time. If I return to it, we will waste time and feed it to the end. But what we can do, a little numerical experiment that Melody has already verbalized. Can you
We
repeat?
turn it into summation.
No. 3 features before. When I was asking, what are we going to do today? And you all were looking, or some of you were looking at the.
Oh,
Look at your script of
the,
what you
we
said
applied
earlier.
the Hamiltonian to, wait. To the ground state.
Okay. Why do we need it?
I don't know.
Me too. It is absolutely useless. I do not see any benefit for the goals of the class, but it is one of the simple operations that we can do. An anecdote: drunk man is lost keys,
Someone gets some keys.
and she's crawling under the street light.
Okay.
Then another sober person is approaching, coming. What are you doing? I'm looking for my lost keys. Are you sure that they lost them under the street light? No, but why are you looking here? Because it is much brighter here.
I love it.
So our today class is about that. So it is useless, but it is much brighter. It is something that we can do, a little exercise. And it will give us a little hands-on how to deal with matrix operators that are stored in a form of direct notation. So remember, we were declaring ourselves as friends of green trees, writing very short symbols.
Yeah.
So summation of this Brian cat gives the way to think in the language of matrices, but do not write as big matrices.
Yeah.
And now we will take the matrix, the operator of the Hamiltonian in the matrix form, apply it to the simple state and see what happens. And we know that there should be energy of ground state, Hamiltonian shouldn't change the state, right? But it's better to feel it through Hamilton. And before we go to this derivation, either in PowerPoint or maybe on the board, I will just announce things which I do soon. You know about them, but I'll just declare. How do you homework?
I'm just trying to.
If you're curious where we are in the class, we are in about like 30, 31, and there should be a little less than 45. So 50 is not practical, but by about 45 we will be done. And you see that we need, in addition to oscillator, we do need few concepts more, and they will be as heavy as oscillator, but they will be squeezed. So we need angular momentum, spin, hydrogen atom, and maybe a few other things. And just yeah, examples.
I gave him a delta and he gave us a heart.
So I think it is your votes, right? The hardest task is for Patricia. You see,
How come some of mine are red? Is that just because they are red?
And why are
Or does that mean
somebody's names
something?
blue? Just cause?
because I don't know.
Okay.
Fair enough.
Probably.
Maybe I was thinking about so much.
It's because I think last week Wednesday you were talking about it.
The computation of expectation value was covered first time we were speaking about this code. Eva was a vice coach. Melody was a
That was a good time for us.
champion. And I think I did cut this 5 minutes of your before in front of a blackboard and put it as standalone video
Okay,
to give you more glory.
yeah.
You can go viral. Everyone like it.
So here is your things to write down after you do presentations. And here is the homework.
That's what's due on Monday? The thing
This
for-
coming Monday. Oh, wait,
Basically, you
Yes.
can read it by listening to your classmates. You can just write the answers or type it in the Word. I can try a plan to simplify your life, although you may having a laughter at me or not or being even angry, but the plan is that one person prepares one subject, so we split responsibilities, and then everyone learns from each one, just takes notes and simplifies the effort for the homework. Here, I think the thing is it is last homework, but it is last didactic academic homework. The remaining homeworks will be based mostly on motion towards the projects. And this one deals with operators as matrices. So the first one you basically know from our last class, and then the rest will be just playing with operators and matrices and demonstrate that they're not foreign for you. So it's not the hardest. It's doable. Okay. It's too early to speak about project before we complete this thing, but we can start thinking on our background. So I do have a list from the previous years, and I have more ideas than pens if you do not know what to do. Right? So I'll go over all of them, and it will be dedicated class when I will just overview possible projects, and you find what you want to do from what is offered, or you will design your own project. But I have an idea that exciton moving between defects on carbon nanotubes can be selected by CHEM. Photo polymerization in 3D printing can be selected by Melody. Two coupled oscillators can be selected by Patricia, although we didn't talk about it. Enzyme catalytic reaction when a molecule comes to iron in the center of porphyrin can be selected by Eva. And then there are polyarones and conjugated polymers can be selected by Fred and Elsa, or we can discuss options.
Okay, what would be related to like cyclic voltammetry? That's what I do for stuff.
Okay.
I don't do anything really with the conjugated
Electron
polymers.
accelerated by electric field, electrochemistry, reduction, oxidation.
Oh, right there.
Okay, so we have kind of an idea.
Yes, we do.
Okay, now there will be some really simple derivations, and they probably will just draw something in the board.
IT guys, we're making fun that there's two screens in here.
Yes.
So.
It was really funny to be here.
Camera is probably camera that the projector is focused on this one. Another one is here.
And then sometimes there's that like, yeah, that was the crusty old one they were talking about.
It's really funny to see everyone walk in here and do a double take when I saw the guys.
I was here,
Everyone
everyone
did
walked
it.
in and I'm like, bro, you don't have class in here, who are you? You're not one of the 5 people in this class. I realized that.
So what should I remember in the middle of the night about the harmonic oscillator and matrices? Me, not you.
Oh,
You do.
then I don't know.
You just do this few homeworks, complete projects, and we stay friends, and
Yeah.
the physical chemistry is done. Oh, okay, there's yet time.
Okay.
When you will take the PCAM2 from Favorite Dr. Herberger. He will give a focus to thermodynamics and statistical thermodynamics. I don't know how he will weight. I prefer statistical thermodynamics. We prefer like more classical with derivatives. But there is a natural question like, can we go directly to the statistical thermo without quantum code? Are they independent or there is a little connection between this class? Like what is the take-home message from this class rather than we get acquainted and do fun projects or just do fun period? There are several problems in the second part of physical chemistry that are based on what we do here. And the examples are so-called partition function. Do you hear about it?
Yes,
Oh, tell me.
I don't know about it. I've just heard of it. I think I learned about it.
With Kenton?
I don't know. I don't think with Kenton.
No?
I don't know what they are.
No, just tell something. You all will be much more prepared.
I'm not a math guy.
Not math, just what is partition function? It has.
I don't know. I've never.
Well,
heard of it
I
before.
know the word partition is like sections.
Mhm.
Well, you should have
Told you
read.
that? Yeah, well, maybe you should have.
Then do it.
It describes the
So-
statistical properties of a system in thermodynamic equilibrium.
I'm speechless because it is absolutely correct.
Such as temperature and volume. They're functions of the thermodynamic state variables such as temperature and volume.
Cool, cool. You should know as trained chemists about Arrhenius.
Yes.
Then everything is easy for you.
Maybe
And yet-
Kenton did tell me.
So some rates of the reaction proportional E minus activation over KT. Did you want to say this, right?
Yeah.
Okay. Now, if we do have many states of a system, and the system like molecules, ensemble, collection of molecules, then each of states may have different energy. And if you want to speak about their probabilities, we need to add together all things like that. Call it, some people call it Z, some call W, some call P. And then by performing mathematical operations over this function, one can get observables. Like in quantum theory, we do observables, quantum observables, expectation values, right? What a dream team did perform and what is recorded on YouTube. So,
No.
and in statistical, one does the following thing, either summation and here a variable corresponding to observable divide by Z. So you weight the value of observable, maybe appropriate for each eigenstate, by probability this eigenstate is populated. And then you get expectation value. So it is two ways of physical chemistry. One quantum, another is statistical. They both target predicting future, predicting outcome of the experiment, but there is a quantum average and statistical average. And
They equal the same thing.
Now you got.
I know that I'm speaking not as a human, but it may be well a sound of a donkey. Sorry.
So there are two different methods of predicting the future. And based on like in polymer science, there are two different ways to determine the glass transition temperature. And one of them gives values that are a lot higher than the other one. But it's the results of the technique So it should be the same case here. It's like there are two different ways of finding the same thing, so they don't always give the same answer.
I will not answer you. I like your train of thought.
It's departing in the right direction.
And I will not give you a full answer, but just a connection. I will do it in dash lines. Like quantum expectation value can be moved towards this formula, and then one can combine quantum and statistical together. Because in quantum theory, we look on the isolated standalone quantum system. And in real life, there are ensembles in many states, and one do average over them. But what is the connection between this course and next course? When you will be practicing statistical sum or partition function, and everyone calls it different way, one needs energies of quantum states for certain systems. Like and there are a lot of successful advertising examples from statistical thermodynamics based on practicing statistical sum partition function for harmonic oscillator. There you will need the energy of the oscillator. So the equation that we are going to practice right now, so energy of state number n equals h bar omega n plus 1/2. You will see the minimal connection from this course and next one that you plug in this into there and then do some mathematical derivation. I hope there will be much more pleasant and interesting thing, but at least it is a minimalistic question. If someone asks, like, what is the connection between quarters here? Oh, sure. Energies goes into partition function.
Dimitri, sorry, I want to ask a question. That n there, does it mean normalization or the number of states?
What?
No, the n in the brackets. Is it n for? Okay.
No, it's not. So index of a state. We have the same indices. Just people like number n because n number, high index.
Okay.
Okay, I'm going to erase it.
Okay.
Okay, and now I have literally 10 minutes back to the subject.
Dimitri, sorry, I'm just a little bit confused. Does it have anything related to what we did last week? That the I was the number operator?
What?
That equation looks like what we did last week.
This one?
No, the energy.
This one?
No, model.
Sorry.
Oh, we are going to do this one right now.
But it was looking like the one we did last week. Does it have something like this? With something like this?
You can't audibly make noises.
Oh, yes, yes, absolutely.
Why am I the only one that has?
So this is this.
Yes.
You're
So
not.
this means this is the
Have to.
normalization.
Still.
No. But
Respect.
You're on such a roll and Dimitri just shut you down.
you did everything correctly except the last word.
Well, you said.
Number operator, not normalization.
Number operator.
Number operator.
Number operator.
I know that by first acquaintance, people look on the outlook rather than what is inside, right? And it could be confusing that here we use letter N and for normalization we use letter N. To avoid this confuse, people use uppercase N for normalization.
I thought the
Is that supposed to
what
be
the
in?
number operator does
an I,
is
yeah.
for normalization.
If you discuss, I need to focus camera on.
Oh, sorry.
Please repeat.
Right. I thought what the number operator does is for normalization.
Something is not quite correct in your train of thought, but I do not know what. I don't know how to correct it. The normalization deals with the shape of the wave function. And here we speak about eigenvalues of energy. So energy and shape of the wave functions, there is a connection, but they're not the same. So when looking at this equation, we should think about energies, not shape of the wave functions. It's not a full answer, but maybe just deviate direction of the train of thought. Okay, 7 minutes. I like when we don't have time. One of our colleagues and friends and here called a theory why people like to delay doing things in time. Because in your and my busy life, there are so many things that needs to be done. And one needs to use a lot of mental energy to rank them, to decide what is more important for today. But if I do nothing and wait until it is really deadline, then I know what to do, what is first thing to do. So
This is given oxidation of the pattern.
Hamiltonian, A dagger A, H bar omega plus 1/2. By the way, we used this equation when we were deriving the functional form of A dagger and A, right? We set it as a connection to momentum squared and position squared. Now, the thing that I didn't derive but declared that in the matrix form, the combination of A dagger A is a number operator. And it means we put here number of quanta. If you do have an oscillator, now I should humbly focus on myself. Oh, it is not visible. Right here. So if you do have an oscillator, and I may miss to draw this function, this little image, but here is your one hump camel. Here is your two hump camel.
Three legs.
Yeah. Three.
And shoulder. Four.
Yeah, oh, yes. So n equals 0, n equals 1, n equals 2. What is the energy of the state? So we just plug in n. So E sub 0 equals h bar omega times 0 plus 1/2. H bar omega divided by 2. E sub 1 h bar omega 1 plus 1/2.
It's gonna be 3/2.
Yeah.
H omega.
Correct.
And then that's gonna be 5/2 H omega.
Yes. So we are going, like, if time allows, my goal is to get this one, but in a very crazy, sophisticated way. Okay,
Oh, okay.
Fancy.
okay, but you agree with this one. So X is elongation, right, of the mode. Here is equilibrium distance. Here is the energy, and this one is potential energy surface.
Okay.
Okay.
So
I'm getting this.
the plus 1/2 bracket h bar omega. So I put ground state bra, then the operator h, ground state cat, and then just opening the brackets. 0, 0. H bar omega can be put outside. Summation n. I'm just speaking up. I don't have a difficult speech, but later on we will have combinations of creation and annihilation operators of more than 2, and then it will be spelled as So it will be like much more like defect of speech. But 1/2. 0, 0. So we can put these things inside the summation. Right?
Dimitri, you put 0 for the expectation value of H because it's the ground states, right? Because we're.
Wait, just wait. We're telling something
What?
smart. I want to focus on you.
And that for the brackets, the 0 for the wave function with 0 is because it's the ground states. Yeah.
Yes, I just it's not equation of absolute truth and everything. It's like a little focused exercise to find the energy of the ground state. Okay. Generous minute.
Ample time.
So h bar omega summation over n. Now we have n, 0, n, 0 plus 1/2. That's it. So this is oversimplified exercise. But how can we think about it philosophically? When we have cat times bra, so it is a dyadic product and it is an operator. Okay? So operator. Here we have bra wave function. Here we have cat wave function. So we have three objects: bra, oper, cat. Now we rearrange them, and we have bra times cat and another bra times cat. So we look on the same object, but in a different order. We regroup them. And bra times cat is just a number. It is a delta. I'm showing it forever.
Thank you.
Delta function. So delta 0n, delta 0 n 0. So these two delta functions will be non-zero only when n equals 0, right? So from all this long summation, we will pick only the values, like in the series, we will pick only the first term. So if n equals 0, so this will be 1, this will be 1, but it is multiplied by 0, right? And then we do have as a result 3 bar omega times 1/2. Okay? And I just want to focus because I suspect you're saying something smart.
I'm really not.
Yes.
Okay, so if you have, like, if n equals any number other than 0, the bras and the kets are 0, how do you get?
If you pick up either one of those. Because here n will be like, if you put n equals 1, this n must be 1.
But would it be multiplied by 0?
No. So here we put 0. Why? I think the question is why we put 0 in here, right?
Well,
No? Oh, yes.
no, so my question is like, n is also in the bras and the kets. So, what?
I was going to announce end of the class, but questions are the best part. So if we can redo this example with bra and cat here being 1 or being 2, and here it is not a number, it means wave function number 1 of x, right? And this bra and cat means like integral or matrix thing. When we do the summation, delta function picks up one element from the whole series. And if the index of the state here will be not 0, will be like 1, 2, 3. If you pick up the factor 1, 2, 3 in here, and if you be promoted here, then you will get one of these.
Okay,
Make sense?
yeah,
Okay. And it is probably the simplest example of this matrix operations. Matrix algebra, some people call it. But you see, it is much more shorthand than doing big matrices.
Yeah.
So camera is focusing there, so meeting is done.
done.
So
Meeting is done.